Hey, the Sioux Falls physics teachers are here with you looking at a conservation of energy problem. So, we have a 0.15 kilogram marble. It's beginning from rest, so we're going to assume zero velocity to start with at point A. Notice from our diagram that point A is 0.8 meters above the ground. We're going to neglect friction here, and the first thing that we're going to ask is, what was the marble's velocity at point B? So let's look at that here first, all right? What we're looking at here using is this, again, our conservation of energy, which says that the kinetic energy plus the potential energy that I start with, so KE1 plus PE1, has to equal the kinetic energy plus the potential energy that I end with, okay? It's the whole idea that energy cannot be created or destroyed. So whatever energy I start with has to be conserved. I have to still have that. Now, that energy can certainly change forms, and that's, of course, what's going to happen here. So let's get into this situation. So KE1 and PE1 is going to basically coincide with the marble being at point A. KE2 and PE2 are going to coincide when the marble is at point B. All right. So at point A, we know that this marble starts from rest, so our kinetic energy to start with is zero. I have zero velocity. All that marble has at point A is potential energy, which is equal to mgh. On the other side of our equation, at point B, the marble is certainly going to be moving at that point, so yes, it's going to have kinetic energy equal to 1/2 mv squared, but it will have zero potential energy because, as you can see from our diagram, point B is at the bottom of the ramp or the incline, and so I'll just go ahead and set that as my zero line, and so it will have zero potential energy at point B. Now, keep in mind, we are asked to find the velocity at point B, so it is that velocity that we're interested in. And we should be able to fill in everything else that we kind of already know here. So plugging in, we know that the mass of the marble is 0.15 kilograms. I'll just go ahead and use the value for 10 here for my gravity. And the height that the marble started at again was 0.8 meters. I'm going to set that equal to 1/2, again the mass of 0.15 kilograms. And I do not know the velocity. Remember, that's what I'm trying to find. So that's my unknown. Now, kind of a thing that we'll visit here in a little bit, but a key thing to kind of note here is that really my masses can cancel out here. I have 0.15 on both sides of the equation. So if I wanted to, I could just eliminate those from both terms. Okay. But in calculating this and solving for velocity, I will end up getting a velocity at the bottom of 4 meters per second.
Okay, so we found down at point B the velocity is 4 meters per second. Next, let's take a look here at point C, which is at the end of the track, and notice that point C, rather than being at the base, the way point B was, point C is 0.3 meters off the floor. So something that is important that'll make this a little different than the last problem is that at point C, the marble will still have some potential energy. It will not have converted all of its potential over to kinetic, but it will have converted some of its potential to kinetic. So let's start by setting this up, and we're going to use the same equation that we did earlier. Kinetic plus potential equals kinetic plus potential. This time, to make it a little bit easier to keep track of the points that we're dealing with, we'll just put the point A in as the subscript, and then we'll have kinetic and potential at point C on the second half of the equation. Now notice that we do still begin with 0 for the kinetic energy, okay? But we do have mass times gravity times height at point A. At point C, that marble will be moving, so our kinetic energy is 1/2 mass times velocity squared. And then next, for the potential energy, which again, remember, will not be 0 in this case, potential energy would be mass times gravity times the height at point C. So now we can go back in and plug in numbers. Again, our mass is 0.15. We'll use 10 as gravity. Height A is that initial height of 0.8. Here's our unknown because it will contain our velocity. So 1/2 mass times velocity squared. And then finally, mass times gravity times height at point C. And it is important to note this is the height of the marble at point C. So this is kind of calculating the potential energy that still remains with the marble. So the height is 0.3 meters. That's how far point C is off of our base level. One common mistake there is to put in 0.5 meters instead, because that's how far the marble will have dropped from point A down to point C. But really what we're trying to calculate there is the amount of potential energy that still remains. Similar to the first part then, notice that 0.15 as our mass is in every term, so we can cancel that out and that will speed up the algebra a little bit. And we find a final answer for the velocity at point C of 3.16 meters per second. Now the last part of this question, hopefully you know the answer to already. Would these velocities be larger or smaller if a 0.3 kilogram marble was used instead? And this shows one of the beauty of using energy to do problems like this when you just have strictly energy terms. So we have kinetic energy and potential energy on both sides of our equation. Mass is included in every term. So if you make a change in mass, yes, you will have more potential energy to begin with, but you will also need to use more kinetic energy for the larger mass that you have. So the mass cancels out, which means that the answer to our last question, would the velocity be larger or smaller? Really neither one. The velocities would be the same if the mass of the marble changed.
Hey, thanks for clicking on this problem. And what we're going to deal with here is another conservation of energy. This is a key concept here. So let's start looking at this one. Little different situation than if you watched our first problem on this topic. Here we are going to be looking at a situation where we know the velocity that an object has at its lowest point on, in this case, a track, okay? And so we know that the car is reaching a maximum velocity of 2 meters per second when it's at that lowest point. And so the question then that we have is, how high up on the track can this car go before it stops? All right, so still using that conservation of energy idea, but now looking at, okay, if I know essentially the kinetic energy that this car has, how much potential energy could it possibly turn that kinetic energy into? So conservation energy again says that let's take our initial kinetic plus initial potential energies, add them together, and that has to equal the kinetic energy and the potential energy added together when we are done. All right, so kinetic energy to start with, again, is going to be 1/2 mv squared. The potential energy that we start with would be equal to mgh. Kinetic energy that we end with, 1/2 mv squared. Potential energy that we end with is mgh. Now, I want to make a point here. This is another again, key point and really a huge advantage of using this principle is that each of these terms contains the variable for mass. Now, I can essentially eliminate that because it is included in every term, which is key here because if you notice in the problem, they never told us what the mass of the toy car was. So I don't really need to know the mass of it. In fact, it doesn't matter because mass is a part of every term here. I can essentially cancel it out. All right, now let's see what we have here as far as what we can fill in. We know that the velocity that this car is traveling at the beginning is 2 meters per second. And so I'll be able to put that in for my velocity. So I'm going to essentially have 1/2 times 2 meters per second. And don't forget to square that. All right. The potential energy that that car has at the beginning is 0 because it's at the lowest point on the track. So I have no potential energy there to work with. All of that kinetic energy then is going to get transferred into potential energy at the end here because we're going to assume that this car goes up the track to a maximum height and stops at that maximum height. So my kinetic energy that it ends with will be 0. I'll have a 0 velocity, and I'm interested in how high up this car goes, so I want to figure out what h is. All right? And so now it's just a matter of simply solving through this equation for what the height is. And when you calculate out height and do the math and the algebra here, you'll get a height somewhere around 0.2 meters tall. Okay? Now again, what that's saying is that an object moving at 2 meters per second, possessing that amount of kinetic energy, will reach a maximum height of 0.2 meters on the track before it stops.
Hello everyone, here's your Sioux Falls physics teachers back looking at conservation of energy. Now we've looked at several examples of conservation of energy already, but this next one has a very key component to it, and that is the fact that you have an object that is attached to a middle point, in this case it's a pendulum, and it is swinging downwards in a circular path. Basically we're still using conservation of energy, but we need to do a couple of important steps to begin with. And you do see quite a few problems that are similar to this, so it is very important that you understand how those steps all work. First of all, we have a little diagram of our situation. The pendulum of the clock is 0.25 meters long and begins at an angle of 30 degrees with the horizontal. Calculate the maximum velocity reached by the pendulum if friction is negligible. Well, the first thing we want to do is add some things to our diagram. Position 1 will, of course, be up here at the start. Position 2 is going to be down here at the bottom, and so that's the 2 points that we're going to be wanting to calculate our energy for. However, if you keep in mind how potential energy works, we need to know the height of the pendulum at the start. And that's where our first important twist comes in. We would want our 0 line to correspond with the lowest point that the pendulum is going to get to. So we're going to draw our 0 line down here, crossing through position 2. Now our pendulum, of course, begins at a certain height here above that. And so our goal would be to figure out how high that is. However, what they tell us is not the height that the pendulum starts with, but rather the length of the pendulum and the angle. And here is a very important addition to your diagram, a little trick that will help these become much easier. When we see a situation like this, notice they've given us the length of the pendulum as being 0.25 meters. Well, when that pendulum reaches its lowest point, it's still going to have a length of 0.25 meters. So what we have then is on our diagram, the length drawn out here at an angle as 0.25 and a vertical line over here also as 0.25. What we want to do is we want to create a right triangle between those two. And so here's our right angle, 30 degrees, that angle is up there. We know that the hypotenuse is 0.25, but notice that this side of the triangle is going to be less than 0.25, and it is going to be less by that same amount of the height. So basically we're taking our vertical line here and we're dividing it into two pieces. One is going to be the height, that's the part right down here, and then the other part is going to be this side of the right triangle that is over here. So now we can do a little bit of trig, because since we have the hypotenuse at 0.25 and we have the angle of 30 degrees, we can figure out this side of the triangle. Notice that that is adjacent, so we would be using the cosine. Cosine of 30 degrees is equal to our unknown side, and for now we can just put in x because that's really not going to have any meaning to us in the conservation of energy part. That's divided by the hypotenuse of 0.25 meters. Then we find that x is equal to 0.2165 meters. And again, you probably don't need to write out all those sig figs, but do keep them in your calculator because you're going to want to use them here in a minute. With that side is 0.2165 meters here, then we can find our height here by subtracting from 0.25. So to find our height, we would take that full length of 0.25, subtract 0.2165, and we find a height of 0.0335 meters. Once we have that height value, now we can return to the actual conservation of energy part.
Okay, if you're still hanging with us here, and I know that part was hard, or just took a little bit of time, but now that we know the height of the pendulum, that it is above the ground to start with, we can go back here now and start using, yes, our conservation of energy. So we're going to say that the potential energy 1 plus the kinetic energy 1 is going to equal potential energy at 0.2 plus the kinetic energy at 0.2, okay? And PE1 and KE1 are going to be where we start our pendulum, and PE2 and KE2 will be at the bottom of the swing. And it is important to note, too, that is in a pendulum motion, the maximum velocity does occur at that bottom point, okay? And that is what the problem, remember, is asking us to find. I know sometimes in these problems we get kind of bogged down in a lot of other stuff. Remember, we are trying to figure out the maximum velocity that that pendulum has. So that's why we're going to use that bottom point. All right, so at the beginning or at the starting point, this pendulum only has potential energy. It's not moving. So potential energy being the mgh. We're not going to worry about kinetic energy at the beginning. That's going to be 0. At the bottom of the swing, it's going to have no potential energy because that's our 0 line, and we'll only have kinetic energy, 1/2 mv squared. Now notice here again, we do not have the mass of the pendulum, but we do not need it. Okay, mass occurs in both terms, so that those masses can cancel out with each other. So really what we're left with is gravity, which I'll just go ahead and put in as 10. Okay, the height of the pendulum, which we just got done calculating at 0.0335 meters, okay, is going to equal 1/2 times that velocity squared. Remember, it is the velocity squared that we are trying to solve for. All right, so working this out and solving for velocity, we end up getting a velocity at the bottom of that swing of 0.818 meters per second. Hey, thanks for joining the Sioux Falls physics teachers here. Problem here is going to look at conservation of energy and work. So now we're going to combine a little work into this idea of conservation of energy. So in this problem, we have a model rocket. It's got a mass of 0.35 kilograms. It's being launched, and it's given an initial velocity of 27 meters per second. And we're going to assume straight upwards, so we're not going to deal with any angles here. It reaches a maximum height of 32 meters. calculate the resistive force that's acting on the rocket to essentially, I guess you would say, slow it down as it moves upward. All right? So, as we mentioned, this is going to be a conservation of energy situation, but now involving some work, okay? And the resistive force that we're seeking here, that we're looking to find, is the force that is basically going to be the result of that work, all right? So here's what we've got set up. We know that the rocket is going to have some kinetic energy to start with. It could have some potential energy to start with. In this case, it doesn't because it's launched from ground level. But let's go ahead and put it into our initial equation here. Plus some work that's going to be done on the rocket. Now, in this case, that work is going to be acting on the rocket, so it's going to actually end up being a negative value for work. But we'll get to that here in a little bit. And we know that has to equal the kinetic energy plus the potential energy that this rocket ends at. And so essentially, again, what we're saying is the left side of my equation is kind of the ground level, if you will. The final result here, or this kinetic energy, potential energy 2, is when we're at that 32 meters, okay? So we know the rocket starts with an initial velocity of 27 meters per second. So kinetic energy, 1/2 mv squared. That 27 meters per second of velocity is going to go in there. So I'm going to have 1/2 mass of the rocket is 0.35 times that 27 meters per second. Okay? Now, I have no potential energy, so I don't need to worry about that. I'm on the ground, so that part drops out. The work that's been then going to be done on that rocket is going to be equal to the force, the resistive force, which is what we're trying to find, multiplied by the distance that that resistive force is done over, okay, or I'm done through, if you will. And then that is going to have to equal, on the right side of the equation, when we reach that 32 meter mark, they do tell us that is the maximum height of the rocket. So we can assume at that maximum height that the rocket instantaneously stops moving and has no velocity. So in that case, I have zero kinetic energy. So the only thing I have to worry about here is my potential energy, which is mgh. So 0.35 is the mass times 9.8 times the height of 32 meters. Okay? And I should also mention here, then, as we look to solve this, remember we are trying to find the resistive force. The distance that that force is done over is 32 meters. So I can go ahead and fill that in here also. All right. And now I'm basically down to a single variable that I'm solving for, which is that resistive force. Now, a little bit different algebra here because I do have some addition in this. So remember that force is essentially going to end up equaling the 0.35 times 9.8 times 32, okay, minus, okay, the quantity of 1/2 times 0.35 times that velocity squared, which was 27. Okay. And when I do that, I should end up with a negative value for my force, which is what I would expect here. Because remember, this was a resistive force that was slowing the rocket down. And indeed I do. I get a negative 0.487 newtons of resistive force acting on that rocket.
Well, hello everyone. Thanks for clicking here with the Sioux Falls physics teachers. What we have today is a problem that kind of uses all aspects that we've talked about with force and energy. A lot of steps. We've gone through most of them before, so do just kind of try and hang with us on the number of steps here. Each one of them, though, should be something that you're hopefully a little familiar with already. What we have is a crate beginning from rest on the top of a ramp. Sliding down the ramp is inclined at 40 degrees. It gives us a coefficient, and we want to calculate the velocity of the crate when it reaches the bottom. Now again, we actually could have done this back when we were studying just forces, totally through free body diagrams. We're still going to need to use a free body diagram again for this problem, but we'll find that if we use energy for other aspects of the problem, it goes a little bit faster than it might have if we were just using forces and free body diagrams to solve the whole thing. To begin with, we need to deal a little bit with that friction amount. It says the coefficient of friction between the crate and the ramp is 0.65. Now, the significance of this is that that friction is going to be taking energy away. Okay, so again, first thing we want to do is mark out some points. Position 1 would be at the top. Position 2 would be at the bottom. So at position 1, it has potential energy. As it slides down the ramp, that potential is converted into kinetic, but some of that is taken away through work done by friction. So the first thing we need to do is figure out how much work is done by friction. And for that, we're going to draw in that free body diagram that we used back when we talked about forces. Basically, we have weight going straight down. And notice that we have 2.5 kilograms. We're going to go ahead and round gravity for 10 today. So that would give us 25 newtons as our weight. That weight is divided into two components. One is the component that pulls it down the ramp, and one is the component that is the normal force. Now again, our right angle is up here, and this 40-degree angle, that's the angle of the ramp, is also the angle at the bottom of this triangle. So if we want to find friction, the force of friction is coefficient times the normal force. And in this case, to find the normal force, that's the adjacent side to the 40-degree angle. So we would say that cosine of 40 degrees is equal to the normal force divided by the weight, which is 25 newtons. And we find that the normal force then is 19.2 newtons. Now we can go back over here. Our coefficient again was 0.65. We can multiply that times our normal force of 19.2. We can then multiply those out and find that our force of friction is 12.5 newtons. And again, that force will be important because it will be doing work on the crate as the crate slides from the top to the bottom.
Okay, now before we can continue on with any type of conservation of energy, we need to figure out how high off the ground this crate starts, because we're going to need that in order to calculate its potential energy. So we're going to need to do a little bit of trig here again. If I just draw another little quick sketch of our ramp, remember this is a 40-degree angle here, and we know that this distance is 1.2 meters, so we need to figure out what that height is. So we're just going to do a little trig here. To do that, just using that the sine of 40 degrees would equal the height over 1.2. Remember, this is my right angle right here. And so I will get a height value of 0.77 meters. Okay, so again, that's going to come in important for me here as I calculate the potential energy that that crate has. Now, looking at our conservation of energy equation, again, we are going to say that the kinetic energy plus the potential energy plus any work that is done has to equal the kinetic energy plus the potential energy that we end with at the bottom of the ramp. Okay? So, we know that this crate starts from rest, so we can essentially then say no kinetic energy to start with. I don't have to worry about that. This crate only has potential energy at its starting point, and so that is equal to mgh, and we know the mass is 2.5 kilograms. Let's just go ahead and put 10 in again for my gravity, and we just said the height is going to be 0.77 meters. Okay. All right, now I need to factor in also the work that's being done. Remember, this is the work of the frictional force that we calculated, okay? And that friction is going to work against the movement of the crate. So that force needs to be a negative value, so negative 12.5. And the work that's done is the force times its distance. So I'm going to multiply that by the 1.2 meters, okay, that it travels. All of that is then going to equal the kinetic energy plus the potential energy at the bottom of the ramp. Well, at the bottom of the ramp, we know there's no potential energy. This is all kinetic. So 1/2 times my mass of 2.5 times that velocity squared. And remember, it is the velocity at the bottom of the ramp that I'm interested in. So I now have kind of a lengthy equation here. It's got a bunch of numbers, so it's just a matter of kind of plugging all this into my calculator and solving for that velocity squared. But when I do, I should get a velocity of 1.9 meters per second. Hi, thanks for clicking on this problem about power. We're going to introduce kind of an introductory problem here on what power is. So in this case, we have a student pushing a couch a distance of 1.25 meters across a floor. It tells this that the horizontal force of that push is 180 newtons and that the time it takes is 3.5 seconds. We're asked to calculate the power that is exerted by that student. Okay, so remember that power is simply equal to, or simply a measurement of the amount of work that is done per unit time. Okay, so think of power as a rate. In this case, it's going to be the work that's done per second. All right, and we know that work is simply equal to the force applied times the distance that it's applied over, and again, divided by that time. And so we're given all three variables there. We know that the force that's applied is 180 newtons, that the distance that the couch moves or is pushed is 1.25 meters, and that the time it takes to do all this is 3.5 seconds. All right, so calculating all of that out, we get a power of 64.3 joules per second. Okay. Another way of expressing that, or another unit that we've talked about, is using the unit of watts. Okay, and so I could say this is also 64.3 watts.
Well, hello everyone, and welcome to another Sioux Falls Physics Teacher problem about power. We have an elevator traveling upwards with a constant velocity. Calculate the power exerted to move the elevator. Now, the first thing that you might notice is that normally, when we think of power, we think of power being a rate of work over time. However, there's no actual time given, there's no distance, so we can't figure out a work amount. If you remember, we did talk about the fact that work can be broken down into force times distance. If we put those two together, we find that power is really equivalent to force times the rate of distance over time, which is velocity. Now this equation, by the way, force times velocity, is on your equation sheet. And it is incredibly important for situations like this where you cannot find an actual value for work. We will never know how many joules were exerted as the elevator moves upwards, but we can find a power amount. Well, once we have that, the power is equal to force times velocity. This becomes a very simple problem. Force for a constant velocity would simply be equal to the weight of the elevator. So if we have 525 kilograms, multiply that times gravity, we'll round that to be 10, and then multiplied times the velocity of 2 meters per second. The power exerted to move the elevator is 10,500 watts or joules per second.